All right, now we're going to just do a simple example. How much pressure is required to pump water at a rate of 50 kilograms per hour through a 75-meter long pipe whose diameter is 1 centimeter? So in order to do that, we need to get, U. So we first need to figure out what U is, U bar. And we can do that because we know m dot. So m dot is equal to the 50 kilograms per hour. And so U, and that, m dot we know is equal to rho times the volumetric flow rate. And the volumetric flow rate is the average velocity times the area of the pipe, the cross-sectional area of the pipe. So we know that the cross-sectional area of the pipe because we know the diameter, and we no longer screw up calculating areas of circles. So it's 7.85 times 10 to the minus 5 meters squared. And so that's my area. So I solve this all for U. I get U equals that 50 kilograms per hour over 1,000 kilograms per meter cubed. That's my density of water, 7.85 times 10 to the minus fifth meters squared. And if you don't screw up, and if you remember to change your hours to seconds, you get 0.177 meters per second. So that's my average velocity in the pipe. In the fully developed region, we determined that we have relationships for U bar to pressure gradient. So U bar is equal to minus G R naught squared over 8 mu. That's something that we solved for last lectures. So we can use that now to solve for the pressure gradient needed to create a particular U. So that's what we're going to do. So we're going to rewrite this in terms of G. So G is equal to minus U times 8 mu over R naught squared. So I have all those numbers. So I'm going to plug all those numbers in. I get G is equal to minus 0.177 meters per second times 8 times 1 point times 10 to the minus 3 kilograms per meter second. That's my mu for water. And then I have in the denominator 0.005 meters squared, which is my R naught squared. And when I crunch that in my calculator, I get negative 56.64 kilograms meters squared seconds squared. But that's kilograms meters per second squared, which is a Newton, times 1 over meters squared, 1 over meters. So that's pascals per meter. So the gradient, the pressure gradient, is minus 56.64 pascals per meter. And so if I want the total pressure, I need to multiply that pressure gradient, minus 56.64 pascals per meter, times the number of meters I'm trying to push this fluid. So I'm trying to push the water for the entire length of the pipe. The entire length of the pipe was 75 meters. And that's going to be the amount of pressure gradient I need for the whole thing. So that's going to be delta P is going to equal negative 4,248 newtons per meter squared. So 4,248 newtons per meter squared from the inlet to the outlet will drive that flow through the pipe if the flow is fully developed. So is the flow fully developed? If the flow is not fully developed, I don't actually have good relationships for pressure and velocity. So I'm going to check to see if it's fully developed. Is it fully developed? All right, so in order to do that, I know it's not going to be fully developed at the entrance. At the entrance, it's going to have an entrance region, and it's going to be of LE, and that's going to be of size 0.06 times the Reynolds number based on D. So I'm going to calculate now my LE. So the first thing I have to do is get my Reynolds number. My Reynolds number based on D is my velocity times D over nu, which is equal to 0.177 meters per second times 0.01 meters which is my diameter. Yeah, that's right. 0.10 is my diameter, and then 1 times 10 to the minus 6 is my nu, meters squared per second. So my Reynolds number based on that is equal to 1,770. So I have a Reynolds number of 1,770, and I can now plug that in to this equation and solve for LE. So LE, the entrance length, is equal to D times 0.06 times 1770, and D is 0.01. So that comes out to be about 1 meter. So the entrance length is about a meter, where this is 0.01 meters for the diameter. So is it fully developed? Well, yes, basically it is. The pipe is 75 meters long, so L pipe is much, much greater than LE. So while there is an entrance region, it represents, almost about 1% of the total length of the pipe. So I'm expecting that my calculated pressure drop that I need is going to be within about 1% of the correct answer, since only 1 meter out of 75 meters of pipe is not in the fully developed region. So to put it another way, fully developed is much, much greater than the entrance region. So I can treat the whole pipe as fully developed, or at least approximate it as such, because, as I said, I calculated LE, entrance length is only 1 meter, the whole pipe is 75 meters long, so 74 meters of pipe is fully developed and only 1 meter isn't.